Welcome back to the History of Being Human podcast. I am the host, Noel Armstrong. We're the only podcast that freely and frankly admits that there are more things in heaven and earth than are dreamt of in our philosophy. It's actually one of the most famous lines from Shakespeare, Act 1, Scene 5 of Hamlet. Hamlet has just seen his father's ghost. He tells Horatio about it, and Horatio says, "Oh, day and night, but this is wondrous strange." And Hamlet responds, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." Now, if you've listened to some past episodes, you know that I'm a big fan of admissions of the fallibility of human understanding. But Hamlet is taking it a little further. He's not just saying, we don't fully understand all the things that we see around us. We don't understand gravity, we don't understand bat sonar, and so forth. No, what he's saying is, there are more things that we haven't even dreamed of. We have no concept of their existence. So it's not even to the point where we could try to understand them. We are completely unaware of them. And there must be a nearly infinite number of those things. Of course, the reason I can make that statement is because it is evidence proof. You could never prove me wrong. To illustrate that, I want you to try to add up all of the things that you don't even know exist, that you're completely unaware of. Just count them up. And you see it's completely impossible. Now, if I'm going to be honest, of course, the converse is also true. We might be aware of every single thing in the universe. Even if we don't fully comprehend it, at the time I'm recording this podcast, human beings might have an awareness of every single thing in heaven and earth, and there would be no way to prove it wrong. You could say, well, in the past we didn't know about dark matter, we didn't even know it existed. Well, we know it now. In the past, we didn't know about bat sonar. Well, we know it now. So you see the logical impossibility of proving that we are unaware, that we have no inkling of the existence of any specific thing. But of course, the point that Shakespeare was making through Hamlet was not some formal logical point. It was more of an emotional appeal to Horatio, not to reject Hamlet's testimony just because it didn't fit with his preconceptions, with his current worldview. Well, today we're going to talk about a topic that doesn't fit with most of our preconceptions. Doesn't even fit with the dominant Western paradigm. It's one of the strangest, most counterintuitive, bizarre, and baffling phenomena in existence. I'm speaking about quantum entanglement. Just how strange is quantum entanglement? Well, let's put it this way. One of the most brilliant physicists of all time, Albert Einstein, couldn't wrap his head around it. He called it spooky action at a distance force. He's using language of the supernatural. Quantum entanglement was just as bizarre to Albert Einstein as Hamlet seeing his father's ghost was to Horatio. It didn't fit into his paradigm any better than Hamlet's father's ghost fit into Horatio's paradigm. Why is that? Well, ever since the time of Newton, let's say the early 1700s, since the time of Newton, physicists saw the universe kind of like a giant mechanical clock. After being wound, set into motion, the clockwork universe ticked from one moment to the next with complete regularity, completely predictable. Effect followed cause, and it never varied. It was a way that could be described in mathematical formulas. So Newton came up with elegant mathematical formulas to describe the workings of this very regular, very predictable clock that was the universe. When Einstein came along with his theories of general and special relativity, he didn't completely overthrow the Newtonian idea of the universe as a giant mechanical clock, very predictable, effect following cause, regularly, predictably. Instead, what he said is there's no one universal clock in charge of everything. Everybody from their relative position has their own clock, but it's still a clock. If you know all the variables, you know exactly what's going to happen. It's still predictable. It's still regular. It's just that there's more clocks than one, I guess is one way to look at how Einstein saw the universe. But here's the key to both of their views. If you knew every single variable, you could predict exactly what was going to happen next. For both Einstein and Newton, if by some miracle you were able to understand the complete state of the universe right now, if you know where every particle is, how fast it's moving, what direction it's moving in, then according to both Newton and Einstein, you could in principle use the laws of physics to predict every single thing about the future. The universe would not act arbitrarily. It would not act randomly. Effect would follow cause, and you could predict exactly where everything would end up. And in much the same way, if you knew every single thing about every particle in the universe right now, you could work backwards to understand what happened previously, and before that, all the way back to the beginning. In both cases, it was a regular, orderly, wonderful, and beautiful universe. Unfortunately, it was also a universe of complete fiction, because then along came quantum mechanics. Quantum mechanics demonstrated that not only do we not know the position, motion, momentum of every particle in the universe, we can't know it. It is fundamentally unknowable. You can know where a particle is, but you won't know which way it's going. And you can know which way a particle's going, but you won't know where it is. You can't know both of those things perfectly. All you can tell is a probability of one thing or another occurring, not certainty. Certainty's gone. Statistical likelihood is the best you can get. Heisenberg's uncertainty principle quantified that. The more precisely you know the position of some particle in space, the less precisely you can know its momentum. And vice versa. The more precisely you know its momentum, the less precisely you can know its location. So imprecision, uncertainty, is built into the fundamental nature of reality, according to Heisenberg's uncertainty principle. And so again, it's not that we don't know everything about a particle. It's that we can't know everything about a particle. And if we can't know everything about a single particle, how are we going to possibly, even in theory, know everything about the universe? What that means is that we can't predict with total certainty the outcome of even the simplest of experiments, let alone the evolution of the entire cosmos. And Einstein, frankly, hated that. He said, God doesn't play dice with the universe. He rebelled against this idea pretty much till the end of his life. Because quantum mechanics tells us, even if you know every single thing you can possibly know about a single particle, you can't predict its behavior with absolute certainty. All you can do is give a range of possible outcomes. And that idea is why Einstein thought it sounded like playing dice. If you roll a pair of 6-sided dice, you know there's a range of possible outcomes. You're going to get something between 2 and 12. You're not going to get 1 or 0. You're not going to get the number 27. But within that range between 2 and 12, you don't know exactly what's going to turn up. And in a similar vein in quantum mechanics, when you conduct an experiment, there's a range of possible values. You don't know exactly what's going to turn up. It is no longer a deterministic universe. It is a probabilistic universe, and a probability is the most certain you can ever get. And even though Einstein didn't like it, decades of extremely accurate experiments have backed that up. It's no longer tenable to hold that we have a clockwork, deterministic, 1-to-1 ratio cause and effect universe posited by Newton and Einstein. To put it very briefly, the universe isn't a clock. Now I have to pause for just a moment and, as an aside, consider the ideas of people like Robert Sapolsky and Sam Harris who believe that we have no free will. They believe that if we knew all of the determinants, their word not mine, of human behavior, we could predict very accurately 100% how a person would behave in any given situation. And I just have to say, in light of quantum uncertainty, this seems like a hopelessly naive and idealistic idea, that you could predict something so complicated as conscious behavior when you can't even predict the outcome of the simplest experiments. That might be the topic for another episode, but I can't help asking the question now. So let's go back to the nature of the universe. We just reviewed one way in which quantum mechanics upset the apple cart, the classic physics apple cart, and that was the idea of certainty, of cause following effect in a deterministic manner. But there were other ways that it challenged our fundamental ideas about reality. Even though Newton and Einstein disagreed on many points, there were some things they thought were self-evident, too obvious even to be questioned. Even a non-scientist understands these things to be self-evident. And one of those things is space itself. Whatever space might be made of. The one thing we know about space is that that's the medium that separates one object from another. That's how we tell these are two different things. There's a space between them. And when things are separated by a space, we assume they act independently. If you see two cars driving down the freeway, one far off in the distance on the right side of the road, and another very close to you on the left side of the road, you understand that they're not the same vehicle, they're not the same car, because we understand that things that are in different locations in space are different things. And if one object is going to influence another object, it has to do that through somehow negotiating the space between them. If one of those cars was to influence the other car, it could do it by driving, closing the distance between them, and crashing into the other car. It could honk its horn and set off a pressure wave that carried information from one car to the other. It could flash its lights, and the photons could reach the other vehicle. But no matter what, in order for one of those vehicles to influence the other, that space between them has to be bridged in some way. Same thing with people. If you want to influence another person, you can speak to them and make sound waves that reach them. You can tap them, slap them, change the temperature in the room by your body's presence. But no matter what you do, you can't influence another person, and by extension, nothing can influence anything else separated from it by space unless something travels, bridges the distance of space between them. And as intuitive, as self-evident as this is, it has a name. In physics, it's called the principle of locality. And in classic physics, the physics of Einstein and Newton, that principle is held to be inviolable. An object could only be influenced directly by something in its immediate surroundings. It has to be local, in the vicinity, in other words. That's the principle of locality. Not only can you not move or change something if you aren't local, you can't even receive information about any other object unless something bridges the distance between you. And now here's the key point. The fastest that any information can travel, the fastest that any object in the universe can influence any other object is only as fast as the fastest thing in the universe. And according to Einstein, that's the speed of light. Information can't travel faster than the speed of light. Influence can't travel faster than the speed of light. The speed of light is the absolute upper limit of how fast something can influence something else across space. And so the obvious corollary of that is, the greater the distance between two objects, the longer time it takes to cross that distance. That's why we see 4 billion-year-old light from stars that are 4 billion light years away. We don't see current conditions. We see conditions 4 billion years ago. The farthest object that has ever been detected by a telescope is called HD1. That's a galaxy that is 13.5 billion years away from us. That means the light our telescope is picking up is showing what that galaxy looked like, the light that it emitted 13.5 billion years ago, just 330 million years after the Big Bang is posited to have occurred. So not only is it the farthest away object ever detected, it's the youngest object ever detected. It might be a supermassive black hole by now if we could see current conditions. We just don't know. We're seeing it 13.5 billion years ago. And again, because in classical physics, light itself is the fastest thing in the universe. No information, no influence, no effects can be exerted any faster than the speed of light can travel. And again, there's nothing especially baffling about this. It tends to be the way that we all see the universe. That's the way we understand the universe works. Enter now quantum entanglement. That's right, the name of today's episode. Quantum entanglement has challenged some of our ideas about locality, to the point that, again, Einstein referred to it in the language of the supernatural, spooky action at a distance force. Now, I want to be as clear and concise as I can about what quantum entanglement is. And I want to get away from exaggeration and hyperbole, because quantum entanglement is spooky, but it's not voodoo. It's not you stick a needle into the chest of a voodoo doll and someone on the planet Venus has a heart attack simultaneously. That's not quantum entanglement. That's voodoo. It's not, I can tell my identical twin just fell in love on the planet Venus while I am here on the planet Earth because we have an ESP connection. That's not quantum entanglement. What quantum entanglement experiments have shown so far is that measuring certain properties of a given particle can be subtly intertwined with measuring the same properties of another particle, no matter how far away it is. In other words, something that we do over here can be subtly entwined with something that happens far away, over there, without anything being sent from here to there, without anything having to bridge the distance at or slower than the speed of light. No matter the distance, nothing needs to bridge that distance. So something that happens here is entwined or entangled with something that happens there. I know that's confusing, but it's also earth-shattering. What we're saying is, intervening space, no matter how great, no matter how far the distance, intervening space does not ensure that two objects are truly separate. That's what quantum entanglement holds. Very careful and precise experiments have demonstrated that the universe admits of interconnections that are not local. Something happens here that's entwined with something happening very far away, even if nothing travels between the two objects. Nothing bridges that distance. Distance is no longer thought to ensure separation. As one scientist put it, from the standpoint of their entanglement, notwithstanding the many trillions of miles of space between two particles, it's as if they are right on top of each other. So let's go back, let's pause for a minute, and talk a little bit more about what entanglement actually is. What is quantum entanglement? And to understand that, you have to go back to the last episode, Schrodinger's cat. There was an idea in that episode presented called superposition. And we said that counterintuitively, until you open the lid of the box and see the cat as either alive or dead, the cat is both alive and dead in that box. That's superposition. The cat exists in both states at once. A simple example would be a coin toss. You flip a coin in the air, let it land. You don't know if it's heads or tails until you observe it. Quantum superposition would mean that the coin was both heads and tails, and it's the act of you observing it that causes the superposition to collapse down to one or the other, either heads or tails. Until you look at it, it's both. Well, both the example of the cat and of the coin toss are examples of superposition existing in one place. The same object, in this case the cat or the coin, is in a state of superposition between heads or tails or alive and dead. And again, let me just reiterate what I said in the last episode. Don't try to understand that. That's the counterintuitive nature of superposition. How can a cat be alive and dead? How could a coin be both heads and tails? If you think you get it, if it makes sense to you, I dare say that I haven't explained it very well. That's superposition. Superposition is an example of something happening in one place. Quantum entanglement is a superposition of more than one particle that can be in more than one place. And if that's confusing, I'm going to give you an example that lays it all out for you. Let's say that you and your grandmother both love Jimmy John's. You call Jimmy John's and you say, deliver 1 roast beef and 1 chicken sandwich, 1 to me and 1 to my grandma. You don't know which one's going to go where. You love both kinds. You don't really care. Bring 1 to me and 1 to my grandmother, you tell the delivery guy. So you get your sandwich, you open the box, and you find out that you have a roast beef sandwich. You know right then that your grandma got a chicken sandwich. You don't even have to wait for her to call you, assuming you trust the delivery guy and so forth. You know she got a chicken sandwich. Information does not have to travel between you and your grandmother, even at the speed of light. Faster than she can call you on a cell phone, you know she got a chicken sandwich because you got a roast beef sandwich. Your order was entangled. There's a formula. Total order equals roast beef plus chicken. When you get roast beef, you already know because of that formula that your grandmother got chicken. Now with the quantum realm, what really would have been happening is your sandwich would have been both roast beef and chicken until you collapsed the superposition by opening the box and looking at it and saw that it was roast beef. And by that same token, grandmother's superposition of roast beef and chicken sandwich would have collapsed into chicken. That's where this entanglement stuff gets really, really weird. No matter how many billions of miles away you and your grandmother were. Let's just call them Schrodinger's sandwiches, not Jimmy John's. Schrodinger's sandwiches. Roast beef and chicken superposed. When you look inside your wrapper and see that you have a roast beef sandwich, your superposition of chicken and roast beef collapsed. But by that very fact, your grandmother's superposition of roast beef and chicken sandwiches can only collapse to chicken, even if you are in galaxy HD1, 13.5 billion light years away, and your grandmother's here on Earth. You already know it's impossible that her superposition collapsed to roast beef, because yours did. That's what entanglement means, no matter how far away. Nothing has to traverse the distance. No information needs to travel at the speed of light. These sandwiches are entangled. And now with that sandwich understanding, let me give you a real-world example. An example of an experiment that's actually been run. And really, I probably should have just led with this because it's also trivially simple to understand. Let's say you shoot a photon at a splitter. This is a 50-50 splitter. It's going to send the photon one direction or another. Let's say path A or path B. So you know that after the photon encounters the splitter, it's either going to be in path A or path B, which means one of two possible conditions will exist. Either path A will have a photon and path B no photon, or path B will have a photon and path A no photon. That's what common sense tells you. But the truth is, quantum superposition means there is both a photon and not a photon in path A, and both a photon and not a photon in path B. And it's not until you detect the photon that that superposition collapses and the photon is either in path A or path B. And what entanglement would tell you is, no matter how far down that path, let's say that these path A and path B are totally divergent. They travel very far away from each other. And it's not for, say, 5 years that you measure and you find out which path the photon is in. As soon as you know that the photon is in path A, you already know that the photon is not in path B, instantaneously, right then. Right as soon as that superposition collapses, the photon is in path A, the superposition of path B collapses with no photon. There are a whole host of specific explanations and ideas around quantum entanglement that are far too difficult for the scope of this podcast, and far too difficult, frankly, for my poor brain to understand. Suffice it to say that entanglement is a phenomenon that has been experimented on at the particulate level, the level of individual particles. There are ways to create entangled particles. One of those is to cool the particles and put them so close together that their quantum states overlap. They then become entangled, and you can conduct experiments on them. You could also split a single photon into a pair of photons, and they will be entangled because they split from the same photon. Nuclear decay apparently produces entangled particles. All of that is beyond the ken of this podcast. But lest you think that this is just useless information, something really quirky and weird and awesome about our universe, there are practical applications of quantum entanglement. So far, one of the most promising and closest to being realized is cryptography. Let's say that a sender and receiver, say on the moon and Earth, wanted to build some kind of totally secure communication. They would just have to include pairs of entangled particles. The sender and receiver could use those entangled particles to generate private keys to decode the messages. And here's the beauty of it. If somebody tried to intercept those keys, tried to discover those keys themselves, they would have to measure the particles. Well, measuring the particles changes their state. And so it would be impossible for them to hack the system. If they tried to measure the particles to discover the keys, the entanglement would break and the sender and receiver would know right away that they'd been compromised. Another application that you hear a lot about is quantum computing. Now that's a topic for an entire episode on its own. So let me just give you the TLDR. Too long, didn't read or didn't listen in this case. Quantum computing would be made possible by taking large amounts of entangled particles and having them work together to solve very complicated problems, much more complicated than our current binary computers could solve. Just how much more powerful is a quantum computer? Well, according to livescience.com, there's a new generation of technology in quantum computing that would make a computer 158 million times faster than the most sophisticated computer in existence today. And think about that. This is just a nascent, a very immature technology. IBM created a chip called the Eagle with 127 qubits. They put it head-to-head with the supercomputer in Berkeley Laboratories, and the Eagle chip won. It was faster. IBM has now created a chip called the Osprey with 433 qubits, exponentially more powerful than the Eagle chip. So this is a technology that's just beginning, and the power of this technology should be obvious. It's really staggering, and frankly, it's a little scary. I mean, with that kind of power, that kind of processing speed, does it really seem likely that human beings will be directly involved in the planning, the creation, the carrying out, the execution of almost anything, except for maybe a few of our own quaint and obsolete projects? The only question to me is, are we going to be benefited by the technology, or are we going to be paying for it at that point? Are we going to be using it to solve problems, or make intractable new ones? And with that, I'll go ahead and close the podcast. This has been the History of Being Human podcast. I'm the host, Noel Armstrong. Thanks again for listening. If you have any questions or comments, feel free to write me at thobhpodcast@gmail.com. thobhpodcast@gmail.com.